Good afternoon, everybody. Welcome to the McKinney Amateur Radio Club's weekly, as it's turning out, Amateur Extra Prep class, licensing prep class. I'm Bob, K5CRX, and this will be session number 4 of a 10-session series. We'll be talking tonight, or finishing up tonight, what we started last week on transmitters and modulation, and then hopefully we will complete the topic of amplifiers and power supplies. A little bit more technical stuff when we get into that one. And then next week, the big one will come up with receivers, a lot of new information for that, a lot of terms and so forth. And I think that will be an interesting session, but a little bit more technical maybe than some of the ones that we've covered up to this point. So with that, we'll wait for everybody to finish logging in here, and then we'll get started. Stand by. Pretty soon. Okay, welcome everybody. Glad everybody's here. Looks like we got a pretty good representation, and I'm guessing we'll probably have several more that will check in along the way, and of course that's a good thing. For whatever reason, I was looking ahead and thinking about the receivers world and the questions that have been added to this exam regarding receivers that almost make you think you're trying to be an engineer and design receivers. A lot of good information, but my goodness, it's a little bit technical. So I've got a couple of handouts that I've done on that this week, actually finished up today. So probably tonight or tomorrow, I will email that to the group mailing list there, so you'll have some extra things to look at when we're talking about receivers and filters and such next week. Sometimes, as one of you just got through saying, that a picture's worth 1,000 words, and I've added a couple of pictures to some of the slides, and then some of these handouts have some pictures there that help to explain various things, intermodulation, things like that. So hopefully those will help, and it'll make it easier for everybody next week when we get to that one. Okay, with that then, excuse me, last week we had gone through the material on transmitters excuse me, goodness gracious, transmitters and modulation. And now we're going to go back and actually go through the questions, and then we'll try to take up amplifiers and power supplies and get through those tonight. And I believe that we'll be able to do that without too much strain. So with that, let me share my screen with you and kick the slide presentation into present. All righty. Another one coming in, and that's good. Okay, give that one just a second there. Okay, we'll do this pretty much as we've done before. In this particular slide deck, we ask the question first, go through the answers, and then there's an explanation following, and by way of review if we need to do that. Like as I said, we covered all the technical information on this last week, but we didn't actually go through the questions. So now we're actually reviewing the questions. So here we go. What is the modulation index for an FM signal? Come on, machine, let's work. Ratio of frequency deviation to modulating signal frequency. In other words, the amount of deviation that comes out with the actual signal that's radiated in relation to the frequencies of the modulation signal, such as, we put out 146.52, the output frequency, and 3 kilohertz modulation, for example, would give us that deviation index, or modulation index, excuse me. Okay, I don't think we need to talk too much about that. How does modulation index of a phase modulated emission vary with the RF frequency? Actually, it does not. It's one of those where the not answer is the right one in this case. Those two don't affect one another. Modulation index for an FM phone signal, a max deviation of 3,000 hertz either side of the carrier frequency. The highest modulating frequency is 1,000 hertz, or the audio frequency is 1,000 hertz. So the output RF frequencies vary or deviating by 3,000 hertz plus or minus, and the modulating index is up to 1,000 hertz. We simply just divide the deviation by the audio, so it comes out to an answer actually of 3, which is pretty easy. You can, if you want to remember the formula, you can do that. Or if you just want to remember the answer 3, there's 2 threes in a row here, by the way. You'll see that come up here in just a second. Modulation index, an FM phone signal, maximum deviation, 6 kilohertz. Modulating frequency is 2 kilohertz. Again, 6 divided by 2, plain and simple, is 3. Keep it simple. And then we'll have another one a little bit later on, but it's some different numbers, but you'll recognize it when we see it. The highest modulation index permitted at the highest modulation frequency for angle modulation before 29 megahertz. In other words, the HF band, a 1.0 index is the highest that's permitted on HF 1.0. That's just a rule. Deviation ratio, as opposed to modulation index. Deviation ratio, the ratio, maximum carrier frequency deviation to the highest audio modulating frequency. Boy, get a mouthful saying that. Okay, important to set the deviation ratio properly. Of course, as we said, the ratio is the ratio of maximum carrier swing to the highest audio frequency coming in. Deviation ratio for an FM phone signal with maximum swing of plus or minus 5, and the highest frequency is 3. That's the other one I was talking about. So here we have 5 divided by 3, which is 1.67. Again, if you like to you want just to remember the answer, memorize the answer, that's fine, or you can do it if you want to. And then this is the last one of those, a 7.5 frequency swing or deviation, and modulation frequency of 3.5 kilohertz. 7.5 divided by 3.5 is 2.14. It's interesting, it just happens to be pi, as a matter of fact, but that's neither here nor there, I guess, really.
Pi it is.
Okay, one of those things. What is frequency division multiplexing, or FDM? And we talked about that a little bit. That's where we do put some slices in there we call subcarriers, and send the information out on the different subcarriers, which means during we divide the transmitted signal into separate frequency bands, or subcarriers is the way I like to call them, and each carries a different data stream, but it all happens simultaneously, so we get better throughput, as you would understand. And this is where it explains the subcarrier. Each information stream is modulated onto a subcarrier up converting it, which is all ties together. Subcarriers are frequencies off the main carrier frequency. That happens primarily in the FM world. Versus time division multiplexing. In time division, we create slots or time slots, and we send little tidbits of information from each signal in each time slot, and then put it back together on the receiving end. So time division multiplexing, 2 or more signals arranged to share discrete time slots of a data transmission, TDM. And by the way, as always, if you have a question, please say so or stop me, and we'll sure stop and talk about it. Which of the following is a type of A to D conversion, analog to digital conversion? And this is another one again. You just have to remember successive approximation is the one answer they're looking for there. There's some other forms and ways of doing that, but for the answer for this one is the successive approximation. Which of the following is a measure of quality on an A to D converter? Well, when it does its conversion, we want to know how clear or how good it's going to be in the long haul, which means how much distortion is it going to pick up along the way. So the total harmonic distortion is one of the measures for A to D conversion. All right. What technique shows that a square wave is made up of a sine wave and its odd harmonics? And just FYI, if you want that, I found a really nice little article that kind of introduces Fourier analysis. I can certainly include that if you want it, but I had never really dug into that before, how a square wave is really just made up of all the harmonics of a sine wave, and that's done by Fourier analysis, and this little article explains how that actually happens. So as you probably already figured from there, the answer is Fourier analysis. coming from Joseph Fourier way back when. I thought that last comment was interesting, that he had really slow transforms because he was using a pen and a quill. Obviously, where today we have computers that can do that very quickly and show us how those things relate. Okay. Which of the following best describes a signal in the time domain? And we're thinking here in terms, if you were visualizing this, of an oscilloscope. An oscilloscope shows the amplitude of a signal vertically and shows the time that the signal is using up horizontally. So we're talking here in the time domain. So we're looking at amplitude along that timeline. So an amplitude of the signal at different times as we look at it, usually done with an oscilloscope. Benefit of making voltage measurements with a true RMS calculating meter. Remember, RMS is that the equivalent to a DC voltage as far as heating value would be concerned. On a pure sine wave, we can calculate it with 0.707 times the peak value. However, if it's not a sine wave, then we need this meter that will do the calculation for us. It's built into the meter. So RMS is measured for both sine waves and non-sine wave signals. Any kind of a signal, it will take care of the averaging of it to give us that signal out. It would be equivalent to a DC working voltage. What determines the PEP, peak envelope power, which is how we measure power oftentimes with a single sideband? What determines the PEP to average power ratio of an unprocessed single sideband phone signal? Well, it'd be nice if we could use one of those RMS meters to measure that, but that's too high a frequency for a meter to do that. So what determines the average? It's what kind of speech or what kind of information we put into there. Someone who has a higher pitched voice will tend to get a higher average power because the signal would be running a little stronger, versus us with have more bass voices, not necessarily as much so. The speech characteristics determine the PEP to average power ratio. The appropriate, what is the approximate ratio of PEP to average power in an unprocessed single sideband phone signal? Again, this is just one of those hard answers, no calculations, 2.5 to 1 or 2.5 to 1, generally speaking. And they were saying this is close to the 2.5 kilohertz bandwidth normally occupied by the voice range, which is usually 2.5 to 3 kilohertz. If that helps, that's fine. Maybe easier just to remember the 2.5 to 1. Which of the following can be used to generate FM phone signals? And that will always be the same thing. It's a reactance modulator. And the local oscillator is a reactance modulator. Reactance meaning we're changing the reactance, which will vary the frequency of that local oscillator. What's the function of a reactance modulator? It is to give us phase modulation or FM signals by varying capacitance in that particular oscillator. You can rule out the others there because the A is dealing with resistance, which has nothing to do with it. AM signals we're not talking about when we're talking about reactance modulators. We're actually talking FM or phase modulation. So both B and C can't be because of the AM. So phase modulated or FM signals varied by capacitance. It can also be varied by an inductance, but more often it's done by varying a capacitor. Frequency discriminator. Anytime you see frequency discriminator, think FM signals. Frequency discriminator pulls the audio out of an FM carrier. What's added to FM speech channel to boost the higher audio frequencies? And that's the pre-emphasis network. Before it goes out and our normal FM transmitters, we go through pre-emphasis. We emphasize the higher frequencies, de-emphasize a little bit or attenuate a little bit the lower frequencies, and that sends out better on FM. Then on the other end, the receiver will use a de-emphasis network to put the signal back where it started from. Pre-emphasis for higher audio frequencies. Okay. One way to produce a single sideband phone signal. Balance modulator. followed by filter. Balance modulator will actually produce both sidebands and the carrier, and then the filter filters out one of the sidebands, the unwanted sideband, and the carrier, so that you have the single sideband remaining. So balance modulator followed by filter. Which method generates a single sideband signal using digital signal processing, or DSP? Signals are combined in quadrature phase relationship. Anytime you see quadrature, also always be thinking angle or 90 degrees. But anyway, the digital signal processors do other things that the standard analog doesn't do for us. Okay. What type of digital signal processing filter is used to generate a single sideband filter? And this is another one that you just have to remember, is this Hilbert transform. And I had some things when we reviewed it last week, and I don't actually remember where that came from. It came from the man's name, Hilbert. But anyway, that's used to generate the single sideband with a DSP, or digital processor. The term baseband in radio communications is the frequency range occupied by a message signal before it receives modulation, basically the carrier. And okay, which of the following constitutes a spurious emission? Little thing keeps getting in my way on my screen. Sorry there. Which of the following constitutes a spurious emission? An emission outside the signal's necessary bandwidth that can be reduced or eliminated without affecting the information that's transmitted. Spurious signals are those little signals that go either side, generally, of the main frequency that we're working on, that we don't want. Can be caused by any number of different things, which we'll talk more about here. And we'll talk a lot about it when we talk about receivers, about how to filter those things out and get rid of the things we don't want. Anyway, the key there being the emission that's not necessary, but the transmission still goes through, but we generate these extra spikes, or birdies as they're sometimes called, that we really don't want. Okay. What limitations may the FCC place on an aperture station if its signal causes interference to a domestic broadcast reception, that is, your TV or radio broadcast reception for your neighbors, assuming that the receivers involved are in good engineering design? Well, the FCC can say you can't transmit at a certain time of the day. They can give you certain hours when you have to be quiet, basically quiet hours, so that you don't interfere with your neighbors if they determine that the neighbor's equipment is in good shape, that i.e. there's nothing weird about what the neighbor's using. Okay. And then we get into a little bit of the technical stuff, this figure E7-1. What type of amplifier is shown? If you look at the transistor, the top element of the transistor hooked to C2 is the collector. The vertical line in the middle of the transistor circle is the base. And the bottom element with the little arrow point on it is the emitter. We can look at that arrow point and tell which way current is going to flow through that device. Current always flows into the arrow point, so current is flowing from ground up to positive with this particular circuit. At any rate, the common element that's common between the input and the output is going to be the emitter. So that makes this a common emitter circuit, not an emitter follower, which is a whole different ballgame. An emitter follower uses, an emitter follower actually has the collector going toward ground, but this one is a common emitter circuit. A couple more questions about that. What's the purpose of R1 and R2? You'll notice that R1 and R2 are a voltage divider. They're going to set a particular voltage value at the base of the transistor. Hence, they're a voltage divider providing a bias for the transistor, voltage divider bias. And we're not going to worry about Thevenin's theorem today. The purpose of R3, that resistor in the emitter there, provides a little bit of additional bias, so it's sometimes called self-bias. Provides a little bit of bias before R1 and R2 actually get into that involved. How are the capacitors and inductors in a low-pass filter network, low-pass pi filter network? Sorry, excuse me. I need to get rid of that, and I can't. Maybe I can do that. Okay, sorry, I had to make a little screen adjustment. Capacitors, inductors, and low-pass pi filter network arranged between the network's inputs and outputs. We went through some diagrams of that last week. So the key to this one is it's a low-pass filter. Being a low-pass filter, that means the signal will need to go through an inductor. If it were a high-pass filter, the signal would need to go through a capacitor. So to make it a low-pass filter, we will have an inductor at the top of the filter, which the signal will go through. And the input side and the output side, we will put a capacitor to take away some of the high frequency components of that signal as it goes through to make it into a low pass filter. So which one of those says two capacitors? Capacitor between the input and the ground, another capacitor between the output and ground with the inductor in the middle, connected between the two. Kind of a clunky way to say it, but I guess it works. Frequency response of a T network with series capacitors and a shunt inductor. And again, series capacitors are giving us the key to this one. That tells us it's going to be a high-pass filter. The T network means it's shaped like a T. Two series capacitors means there's a capacitor hooked to a second capacitor, and that the signal goes straight through. The high pass or high frequency signal goes straight through. The shunt inductor, there's an inductor between those two capacitors that will take the lower frequencies to ground or take those out. So the T network with two series capacitors is going to be a high pass filter. Purpose of adding an inductor to a pi network to create a pi L. You'll recall the pi L network was the pi-shaped filter, and we put an extra inductor at its output, and that extra inductor out there will tend to eliminate the frequencies that we don't want, the garbage that we don't want, or in other words, harmonic. It acts as a harmonic suppressor. Okay. Again, if you have a question on any of this, please do stop me. Which describes the pi L network. It's basically a pi network, and we add an inductor to it on its output. So pretty straightforward. And characteristics of an emitter follower or common collector amplifier. Now, this is where I mentioned earlier that the diagram that we had there was a common emitter. The emitter follower is a common collector type. It has some specific characteristics that make it valuable for a lot of things, one of which is the signal, it stays in phase going through it. It does not invert the signal. Many of the little amplifier circuits that we use will invert the signal as it goes through. A common collector does not. How does an impedance matching circuit transform a complex impedance to a resistive impedance? By canceling out the reactance part of the impedance, leaving the resistive part to be the desired value there. Okay. It's really the impedance matching has to do with using capacitors and inductors to cancel out what we don't want and leave the resistance part there. What creates intermodulation interference between two repeaters in close proximity? The assumption being here that two repeaters are close together, transmitting on different frequencies, but maybe the frequencies are relatively close together. Most likely that they would be. When they both transmit at the same time, there are two output signals mixed in the final amplifier of one or both, so we get intermodulation distortion between the two repeaters. And they're basically putting out extra garbage, which they're not intended to put out. Okay, what causes it? Nonlinear circuits or devices. Now, the nonlinear devices, in most cases, is going to be some kind of an amplifier, like an integrated circuit amplifier or something like that, ICM. A nonlinear circuit generally is an amplifier. Most amplifiers are nonlinear in these things. That is to say, they are not absolutely one-to-one or one to whatever it is without providing any distortion whatsoever. So the intermodulation is caused by nonlinear circuits or devices. What is the term for the reduction in receiver sensitivity caused by a strong signal near the received frequency? So we're actually talking receivers here just a little bit along the way. So if something's overloading my receiver, it's desensitizing my receiver. I'm losing my sensitivity. That strong signal there is swamping my radio, is another way to say it. Which of the following filters is used in a 2-meter band repeater duplexer? Now, 2-meter band is the key on this one. For that, we have to use a cavity filter. Cavities are physically large, mechanically large filters on 2 meters. Generally, they'll be about 6 inches in diameter and anywhere from about 12 to 18 or so inches long. So they're quite big. But they're special type of filters. This cavity has a very, very narrow pass band, and they're used to filter out the transmitter's information and keep it from getting into the repeater's receiver. So for the 2-meter band, we use a cavity filter. Which of the following is used to reduce or eliminate intermodulation interference in a repeater caused by a nearby transmitter? This is what we were talking about 2 questions back, or a question and a half back, I guess, where the 2 transmitters are close together and transmitting. Then for that, we use this crazy thing called a terminated circulator on the output of the repeater to trap or to take care of that extra garbage that it's trying to spit out, take care of the distortion that it's putting out, the little peaks and intermodulation peaks that it's trying to transmit. What current flows equally on all conductors of an unshielded multi-conductor cable? It's called common mode current. And again, that's one we just have to remember. And common mode current, and that is the end of that particular one. How about that? Okay. All right. That takes care of transmitters and modulation techniques. Any questions or thoughts on any of that before we hit the Chapter 7 and Mr. West's layout anyway? It's a good place to, if you have a question. Nay? All right. Let me bring up the next one, and we want Chapter 7. And I'm going to share the screen, and here we go. Yeah. Okay, are we good, everybody? Okay, let me back one just to make sure. Yep. Nope. I need to back another one, don't I? Wow. I must have hit the, yeah, there we go. Okay, sorry there. I got a little carried away there with the mouse wheel. All righty. Amplifiers and power supplies. There's, again, some technical stuff in here, but I think this will actually move pretty rapidly, and I think we'll be able to finish this one without any real difficulty. Amplifiers for frequencies below 144 megahertz could be purchased in used condition by an equipment dealer and then sold by that dealer to another amateur operator for use in that person's station. This is to prevent the sale of amplifiers that were actually intended for CB use, constructed without the FCC's blessing. In other words, the CB users would take some amplifiers and do some crazy things with them. And of course, CBs were limited to 4 watts, if you might recall. So this was a way that these things could still be done. But by and large, on the wholesale world of things, this prohibits our using a CB amplifier, the CB users trying to use one of our amplifiers. That's the essence behind it. Okay. Recently, FCC revised the policy on RF radio frequency amplifiers. In order for an RF power amplifier to be granted certification, the amp must meet tight spurious emission standards when it's operated at full power. 2 amplifiers with large band switching filter networks meet the specs more easily than the smaller solid state amps. This is why solid state amps are still relatively expensive compared to the tube amps, and the reason you see so many tube amps that are out there. Tube amps are just old and reliable and are rock solid. They just really work well. At any rate, the specifications are very, very tight for spurious emissions. They have to be very clean. You remember, this is an amplifier, so inherently it's going to try, it's a nonlinear device in that sense. It's going to try to generate spurious emissions. So we have to have various filter networks to suppress those spurious emissions. Classes of amplifier. Class A amplifier, that's one that has the greatest linearity. That is, it's operating right in the middle of the transmitter's operational range. However, while it has the greatest linear effect, it also has the least efficiency, only about 25% or so. Usually those are small signal amplifiers where they're like an RF input amplifier, something like that. Sometimes used in modulation circuits where perfect linearity is needed. Input signal varies continuously as the input current over the complete 360 degrees of the sine wave signal. So we have a full 360-degree conduction through the Class A amplifier. Its bias is normally set halfway between saturation and cutoff. You'll remember those two terms. Saturation is when the amplifier is turned completely on, and that's all it can do. Cutoff is when it's turned completely off and no signal flows through it at all. So for this to be a Class A amplifier, we normally have everything set so that the signal is starting out at the halfway point between saturation and cutoff. And this is a little chart to depict that. If you see the load line is that leaning line, or that about a 45-degree line, I guess, called the load line there. And you'll see the Class A amplifier line is set right in the very middle, biased at the operating point for that, so that the signal that goes in the signal that comes out rather looks like the signal which goes in. A Class AB amplifier, however, is biased further down that line toward cutoff. Down at the bottom is cutoff, at the top is saturation. So the Class AB is pushed down a little bit further, and you'll notice that the waveform does not go through the full 360 degrees. The right-hand half of the sine wave is clipped off. For most things, that's not enough clipping to be that noticeable. It'll still work okay. A Class B amplifier, however, is set right at cutoff, so it will only conduct during one half of the cycle that comes in, or 180 degrees. And a Class C is even lower than that, and it will just catch a little peak of the incoming signal and amplify it. It is the most efficient. And there are some amplifier applications where the Class C works wonderfully well, where linearity is not a problem. For example, in FM broadcast, when we send out FM, we're varying the signal, not the amplitude. So linearity is not an issue. However, for voice, that doesn't work well. We'd only get garbage after if we're using a Class C amplifier to amplify voice. Another picture of the same thing. A Class AB amplifier is kind of a combination thing, as you can see there. And this is the answer to the question. Its output is more than 180 degrees, but less than 360 degrees. As you can see from the sine wave, the bottom half of the sine wave has been clipped off. High-powered vacuum tube linear amplifiers use grounded grid topology. If you remember on the tube, you have a cathode and an anode and a grid in between, which controls the amount of flow between the cathode and the plate or the anode. The grounded grid topology is used because it has a very low input impedance, usually around 50 ohms, which makes it great for an RF amplifier, because we'd be feeding it with a transmitter that has a 50 ohm output. So if it has a 50 ohm input, it's a natural for that. A lot of the common tubes, such as 3-500 series tubes, are really designed around being a grounded grid amplifier tube, specifically for that. Okay. Class AB amplifier, just illustrating what it is. You'll see the A is top transistor is amplifying the top half, and the bottom transistor is amplifying the bottom half. Okay, in a linear amplifier, the active device, whether it's a tube, a transistor, an FET, or whatever, and I'm not sure what remove got in there for. I don't know what that's supposed to be. But anyway, functions as a voltage control variable resistance, dissipates energy over the entire RF or audio signal cycle. What are we saying there? We're saying that the tube of the transistor basically acts like a potentiometer, a variable resistor, where a contact slides up and down a resistor and gives you a varying voltage out. And that's really what we're doing with an amplifier. We're taking a varying voltage out. That voltage as it varies, it's controlled by the tube or the transistor, FET, or whatever it is there that's actually doing the amplification. The theoretical efficiency for a resistive loaded Class A amplifier is only about 25%. A switching amplifier, which is a Class D amplifier, the active device is either completely on or completely off. And there are certain applications where a Class D amplifier can be used. Okay, let's see here. In tube amplifiers, RF chokes in the plate grid circuit, small value bypass capacitors, suppressor capacitors in the grid circuit help reduce unwanted oscillations. This is called neutralizing a tube amplifier, by the way. It's to get rid of parasitic oscillations, oscillations that would just occur even when there's no signal there. They would just self-generate garbage, if you please, and oscillate, and that would, of course, be added to your desired signal. So to get rid of that, we neutralize that, as it's called, and we put these different components in there to get rid of those unwanted oscillations. The Class AB amplifier takes the input signal and causes a field effect or bipolar transistor operate near cutoff, but not all the way into. Lead to a nearly linear reproduction, but not quite. You'll remember it clipped off the right-hand bottom part of that signal that was there. The Class C amplifier is operated outside the linear portion of its operation, causes the signal sideband voice signal to sound harsh. So that's just to say that we wouldn't want to use, generally speaking, the Class C amplifier for voice or anything like that. It becomes distorted, as we said earlier. Okay, and I'm not sure why that was in there, but it's interesting, showing a Class C amp nonetheless. Class D amplifier is a switcher amplifier, voice switching technology to give high efficiency. Switching means it's either on or it's off for only brief periods of time. Switching RF amplifiers are very popular in the amateur band, especially the low frequency bands that we have, the 2200 meters, which is 630 kilohertz. Very low. And you can actually use some of the high-end audio amplifiers to work on those frequencies because they're just a little bit above the audio frequency. Need a low-pass filter and are a very high, very narrow bandpass filter to keep the extra garbage out of there, to keep the birdies out and the things that you don't want. Power supplies. Okay, we start talking power supplies and the things that go on. The picture on the left, I'm not totally sure what relevance that has other than to show a transistor that's probably fairly high power, and it has a thermistor mounted to the top of it to monitor its temperature, I guess, so it doesn't burn itself up. And based on the screws on either side and the large traces with which it's soldered onto the board, I presume that's to absorb some heat. At least I'm thinking that's the situation. There's and the formula they're describing gain on how we would get gain. That's just nice to know. Okay, modern VHF, UHF single band or dual band amplifiers. And what we're saying with that is you can get, for example, you can get a dual purpose VHF, UHF combined amplifier that you could feed with a handheld radio, for example. And instead of having 5 watts out of your handheld radio, goes to this little amplifier and comes out at maybe, say, 40 or 50 watts. So anyway, we can have that dual band amplifier. See the lead strength with many small ferrite beads to minimize the parasitics coming down the various lines that go into it. Ferrite beads are always used to minimize or to get rid of parasitics, oscillations, things that you don't want. Unlike switching regulators, analog regulators can only reduce voltage from an unregulated value. And we'll talk about more what that means, and we'll show some circuit diagrams here in just a little bit. This means you need to have a bit more voltage going into the regulator than if you have at the output, i.e., if you have a 12-volt pass regulator, which is what we're talking about here. If you have a 12-volt regulator for that and you want to give a constant 12 volts out, you need more than 12 volts going into it, say 18 or 20 volts, maybe 25 volts even, so that the regulator has plenty of voltage overhead to regulate as it needs to keep the output constant. Typically, the input voltage is 30 to 50% greater than the output voltage for it to work reliably. Linear or electronic voltage regulator varies the conduction of a circuit in direct proportion to the variations of the line voltage or the load current that is needed. In other words, we're talking a pass transistor, a transistor which passes the voltage and current through it on its way to the load. And then that device, usually a transistor, will vary its amount of resistance to keep the output voltage and current constant. So linear electronic voltage regulator varies the conduction of the circuit. That is, it changes its resistance to allow the current to flow through it to keep the output constant. Zener diodes. You'll see down at the bottom of that thing a picture of a Zener diode as it's shown schematically. Has that little squiggly thing across its cathode, which indicates the Zener portion. Normally they're used as a voltage reference. With a Zener diode, you will always see a resistor in series with it. Again, we're using a kind of a voltage divider kind of a thing with it. The resistor allows the Zener to do its job without burning up, by the way. But anyway, the Zener diode has that little zigzag bar to indicate it as you see. It can serve as a voltage regulator by itself, but normally only for very, very low current. In most cases, it's a voltage reference to help some other more powerful regulator give us the kind of regulation that we want. And then note there for the old timers, before the Zeners came around, the voltage reference of choice was a gas-filled tube. You had a tube type reference, just a tube filled with gas, which would conduct at a certain voltage. Switching regulator is regulates voltage by adjusting the duty cycle. That's again, before we were talking about a fast transistor or a linear power supply system. Now we're talking a switching regulator, which instead of doing that, it has internal switching circuits that regulate the voltage by adjusting the duty cycle, the on and off times of a square wave. So we have little pass transistors and filters and all those things running at a high frequency, and they control the voltage by turning on and off at the right times, i.e. adjusting the duty cycle, how long it's on, how long it's off. The output in the rectangular wave, then square wave, is filtered out or integrated to supply an output voltage equal to the average voltage setting of a rectangular wave string. Duty cycle is inside a closed loop, which means it talks to itself and maintains the regulation by adjusting the duty cycle. Okay, very common series voltage regulators used in many high-power linear power supplies, and this is where we're talking about the pass transistor again. With no load, the series regulator dissipates essentially zero power. And under full load, it can dissipate up to 50% of the total power. By contrast, for lower power applications, a shunt regulator is generally simpler. The difference being here, a shunt regulator, shunt means it's hooked in parallel to the output, and it sucks some of the voltage and current to ground. Basically, it siphons off power to maintain regulation, as opposed to a pass transistor or series regulator, which acts as a variable resistor in the series with the load itself. With no load, shunt regulator is 0% efficient, because if there's no load on it, the shunt regulator is absorbing all the voltage and current that it's supposed to regulate, since there's no load there to share that for voltage and current with it. Linear or analog voltage regulators are very clean, but they can be quite inefficient. That's again because you have to have so much higher an input voltage than the output voltage. Must always have a supply voltage significantly greater than the desired output, as we said, dropping to the bottom. In any series circuit, the power dissipation of any component is equal to the voltage difference across that component times the output current. In other words, we're talking about the voltage drop across that pass transistor. That when we say the power dissipation of that component, we're talking about the transistor that handles that. We take the voltage drop across that component, i.e. we have 25 volts coming in and we have 12 volts coming out. The difference would be 13 volts. And then with that, we can calculate the current that it's actually working, providing for us. In circuits where the load on the unregulated input source must be kept constant, we use the less efficient shunt regulator because it will always make sure that we're pulling the voltage down to where it's supposed to be. It won't let it rise. Sometimes you get quite warm, usually mounted on a chassis, but it has a great heat sink on it to take care of it. Okay, finally, we get into some good things here with some schematics and such. This particular little power supply there shows 25 volts on the input, 12 volts on the output, with a pass transistor Q1 handling all of the magic. The Zener diode D1, you'll notice it's a Zener because of the squiggly line that's in there above the anode. The Zener diode is going to provide the reference voltage for Q1 to keep it putting out the right amount of voltage and also regulate the current as necessary. So in this question, this Q1 is the transistor that can handle. Wow, I should have worked on the verbiage here. It's a transistor that can handle can handle a greater current than the Zener diode. That's what we're trying to say. Sometimes called a transistor series pass, used to control the current supplied to the load. Q1 keeps the output voltage constant, and it bases its voltage on that voltage coming out of the Zener diode D1. That'll be a constant reference voltage. C2, notice that's right there across the Zener diode. Basically, that C2 capacitor is going to filter out any ripple that would come in from the 25 volts coming in. If there's ripple that comes in, that is to say, if that power that's coming in there hasn't been cleanly filtered, if there's some ripple there, then that the C1 doesn't catch, that the first capacitor doesn't catch. We don't want that going into the Zener because that will cause the Zener not to be stable. So by putting a capacitor across the Zener, we hold its reference voltage very steady. So to say the answer to the question is it bypasses voltage changes around D1, the Zener diode, to keep the reference voltage stable. And the key there is the ripple frequency. It's filtering out the ripple. Components D1 and Q1 give the answer away. It's a linear voltage regulator. It gives you a solid regulated output voltage. Even though the current changes, it will maintain the voltage constant no matter what the current does. The resistors in parallel across the power supply. This is especially one that has a lot of filter capacitors, a very high current supply. The resistors across that will help to equalize the voltage drops across each of the capacitors. They also act as bleeder resistors when the power supply is turned off. That is, when you turn the power supply switch off, those capacitors will maintain a charge that you don't want it to maintain. So those bleeder resistors will dissipate the charge that's left in the capacitors. And then they add a constant load if there's not much current being taken out of the supply, so that it doesn't create problems for the capacitors with their voltage going too high. Modern high voltage power supply usually contains a series of resistor and capacitor in parallel in the high voltage plate circuit of the tube in order to buffer the initial inrush of startup current. So we put a little resistor in there so that it slows down the charge of that capacitor, basically. This allows the filter capacitors to slowly build their charges so that we don't have arcing inside there and we don't blow up some capacitors. Otherwise, if everything comes up too quickly, the capacitors can act like a short circuit, basically, and arc, which we don't want them to do. So we put a resistor in there to slow that down just a little bit. With no load on the secondary of a transformer. So we're looking at a transformer here. The primary has power on it. The secondary has nothing on it. And at that point, it just becomes an electromagnet. All the current is converted into a magnetic field, since there's nothing coming out of there. Gordon makes the comment that he used to use that to bulk erase reel-to-reel audio tapes because it has a great magnetic field that would actually do that. That's a lot of verbiage, isn't it? Okay. Talking about the conventional heavy transformer linear power supplies. I'd not seen this before, but he said it take for about each 12 or for a 12-volt regulator, for each amp of its output, it takes about 2 pounds of weight to make that happen. So a 20 amp power supply would be about 40 pounds based on that. Wow. Switching supplies. Is about the same cost as the old big transformer supplies, but very small transformer and filter components are used in that because the old big transformer thing with all the big capacitors were big, expensive, and heavy. The switching power supplies can use smaller components because they don't have to stay on as long as switching on and off, and they're much more efficient. Just a picture of a switching power supply made by Jetstream. By the way, that's a nice little power supply. Okay, and with that, we're going to stop that one here. And I'm going to switch to the other deck. So give me just a second here. And that's not where to go. It's still not where I want to go. Okay, I'm not actually going to out here to share this, but I need to call up 07. I'm going to get to chapter 07. That's the right one. Okay, sorry there for the confusion, folks. Take that all the way up. And let me go back to my session. Okay, now. Wow, something just went wrong. Sorry there, gang. Something just went awry and I just lost my whole screen there. Give me a second. Show me. There we go. Sorry. You got to figure out which button to push. I wasn't expecting that. All right. Now then, back to this thing. Let me share my screen and go on and let's go through the actual questions now. Okay, and you'll recall this is where we ask the question first. We have the review information afterward. So we'll go right through the questions and answers. And if you have anything that you want to discuss, please stop me and we will do that. I think we're going to have plenty of time for that. Yeah, I think we will go kind of quickly here. Under what circumstances can the dealer sell an external RF power amp? All that good stuff. It's constructed or modified by an amateur radio operator for use at an amateur station. Meaning if the amateur built it, it didn't have to go through FCC certification. What describes the qualifications for an amplifier? It has to meet the FCC's emission standards when operated either at the lesser of 1,500 watts or at its full power. All right. What is the operating point of a Class A common emitter amplifier? Remember, we talked about saturation and cutoff. Class A says it's right in the middle between being saturated, fully turned on, and cutoff being fully turned off. That makes it linear. What portion of the signal cycle does each active element in a push-pull Class AB amplifier conduct? And you remember we said that it goes over 180 degrees. The top was the full 180 degrees. The bottom half of the cycle was less than 180, giving us more than 180, but less than 360 degrees for Class AB. A grounded grid amplifier, you'll recall, because it's grounded, it gives us a very low input impedance, usually around 50 ohms. Isn't that convenient? All righty. Why are switching amplifiers more efficient than linear amplifiers? Because the devices at saturation are cut off most of the time. That is, it's not conducting all the time, so it makes it more efficient. What can be done to prevent unwanted oscillations in an RF power amp? Most cases, this would be more applicable for a tube amplifier, but we want to suppress the parasitics, which is also called neutralization. Which of the following is likely to the likely result using a Class C amplifier to amplify a single sideband phone signal? In other words, if we put voice through a Class C, which has just a tiny bit of conduction time, it's going to sound terrible. Distortion, It's going to sound awful, and it's also going to make it splatter, make it use a lot of bandwidth. Okay, a Class D amplifier, you'll recall, is a switching type amplifier. Uses switching technology to give high efficiency. All righty. What circuit is required at the output of an RF switching amplifier? We want to make sure we get rid of any harmonics, so we put a filter to filter out any spurious harmonics. What devices are commonly used as VHF and UHF parasitic suppressors at the input and output terminals of transistor ferrite beads? They cure a lot of ills, needless to say. What is the dropout voltage of a linear voltage regulator? I don't think we actually talked about that before. And this is the minimum input to output voltage that's required for it to work. On a linear voltage regulator, remember we said the input voltage needs to be 25 to 50% or 25 to 30% higher than the output. If that voltage is too low, if that goes down too low, that's called the dropout voltage. The minimum input to output voltage required for maintain is that dropout voltage. That's when it gets too low for it to actually regulate anymore. The input is too near the output for it to regulate. How does a linear electronic voltage regulator work? And I hate to have to say my cute answer, it works pretty good. That's not really what I'm supposed to say, though, is it? Sorry. Let's see. What is a good answer for that? The conduction of a control element, transistor, usually our FET or something like that, is varied to maintain a constant output. It acts like a big variable resistor. Electronic regulator works like a variable resistor, really. So the conduction is varied to maintain a constant output. What device is used as a stable voltage reference? And there's only one that works for that. That's the Zener. Zeners come in all kinds of voltage ratings, by the way. You can get a 6-volt Zener or a 6.2-volt Zener, for example, and it would help to maintain the output voltage at that, whatever that is that you're looking for. You select the Zener that matches what you're looking for. What does a switch mode voltage, or how does a switch mode voltage regulator work? It changes the times that the signal is on, the times that the signal is off for the power signal. So it means it's varying the duty cycles. Which of the following describes a 3-terminal voltage regulator? It's just a little old series regulator. All it is a pass transistor encapsulated into a 3-terminal device. Looks like a fat transistor. Which of the following calculates power dissipated by a series linear voltage regulator? That's where we measure the voltage across the regulating device. That voltage difference between input and output multiplied by the output current gives us the amount of power that's being used. Which of the following types of linear voltage regulator operates by loading the unregulated voltage source? So we're going to put a shunt across the output that maintains that voltage at a particular spot. It's called a shunt regulator. They didn't give us a picture of that, unfortunately. Okay, there's our little circuit we looked at before. What's the purpose of Q1? Q1 is the regulating device. It keeps the current, controls the current to keep the output voltage constant. All right. Let's see then. Purpose of C2, that's the capacitor over there across the Zener. Excuse me. It basically filters out any ripple that comes out of that 25-volt supply that might be coming in. So it's taking care of any ripple around D1. So D1 is constant. What type of circuit is shown there? It's basically a linear voltage regulator. What's the purpose of connecting equal value resistors across the power supply filter capacitors? They equalize the voltage across each capacitor. They discharge the capacitor when you turn the power off, and they provide a minimal load on the supply if the supply is not actually doing something, which means they're all correct. Okay, we just hit 8 o'clock, and we're only a few questions away from the end, so if you will, bear with me. Purpose of the step start circuit and a high voltage power supply, so we don't hit those capacitors with all we've got at one time and cause arcing. We don't want the arcing. We want to have the filter capacitors to charge up gradually so we don't blow them up and arc across them. Otherwise, they would act as a dead short when we first got the inrush of current. What is the current that flows in the primary winding of a transformer if there's nothing on its secondary? It's no load. It's basically just a big magnet. So it's magnetizing current. Why is the switching type power supply less expensive and lighter than the equivalent linear power supply with a great big old heavy transformer and lots of capacitors? Because it can use high frequency components that are much smaller, because the filtering is much easier because we're using much higher frequencies. So the high frequency inverter design lets us use smaller transformers and filter capacitors. And that's the end of that. All right, let me get out of that. Okay, gang, we did it. Well, we're just a minute or so over 8. That's not bad at all. Good timing. Any questions, comments, thoughts? We're open.
No, sir. Thank you.
Hey, Bob.
Well, thank you, guys. Appreciate you being here tonight. I'll get this out to Lance here pretty quickly, and it'll be out on YouTube if you want to go back and look at it in a day or two.
Bob, are you there?
Yes, sir. Go ahead.
I missed some of last week's video. Is it recorded somewhere, or am I missing it?
Yes, it is. It's out on the YouTube. If you go to the McKinney Radio Club's the YouTube channel, they're there under classes, I believe, is what Lance told me. But yes, they are posted. All the previous sessions have been posted to YouTube.
Thank you.
Mm-hmm. If you have a problem finding them or whatever, shoot me an email. I'll get an address for a URL for it, and I'll ship it back to you. Okay. Unless anybody doesn't want it, I have some handouts I'm going to email out before next week. For those of you who came in at the very end, might not have heard the announcement. We're talking about receivers and filters, some pretty technical stuff there, some definitions and such that we need to explain, and some of these documents do that. So I'm going to be sending out 3 or 4 different things in an email between now and next week. So unless you tell me you don't want it, you will receive it. I hope that'll be okay. Okay. Anything else from anybody?
Thanks, Bob.
Thanks, Bob.
Thank you.
Thank you,
Bob.
gang. Have a good weekend coming up, and Lord willing, we'll see you next time.
Thanks, Bob.
Okay. Take care, and we're going to terminate the session. Goodbye all.